Higgs boson,
चंद्रशेखर लिमिट,
string theory,
न्यूट्रिनोज,
quantum entanglement.
कुछ समझा क्या?
Ever felt bored and confused while reading lengthy physics textbooks or articles?
Yeah, on God, bro.
I'm Arnav,
And I'm Pratham.
and welcome to Quark Talk, where we decode all the complexities and simplify these intricate concepts in physics.
They may have seemed too complex to understand until now.
So, as we said in the last episode, Einstein's theory of general relativity was introduced in the early 1900s.
But wait, let's back up a bit again. In the 1600s, Isaac Newton contemplated how an apple falls to the ground, how the moon orbits our Earth, and how our Earth orbits the sun. Basically, he concluded that every object with mass must attract every other object with mass. But Newton himself was not satisfied with his own theory at all.
Yeah, so basically he thought that how can masses that are separated by such vast distances apply a force on each other? He wrote that one body may act upon another at a distance through a vacuum without the mediation of anything else is to me so great an absurdity that I believe no man who has a competent faculty of thinking could ever fall into it.
Interesting. But there was one man who definitely had a competent faculty of thinking, who was Albert Einstein. And over 200 years later, he figured out how gravity is mediated. Bodies do not exert forces on each other directly.
Instead, a mass, for example, let's say the sun, curves the space-time in its immediate vicinity, basically around it. This then curves the space-time around it, and so on, all the way to the Earth, let's say. So the Earth orbits the sun because the space-time that Earth is passing through is curved. So masses are affected by this local curvature of space-time, so no action at a distance is required. Mathematically, this is described by Einstein's field equations.
Which is again a topic for another episode.
So that's that.
After that time, basically scientists started thinking about what happens to stars near the end of their lives. And after some research, they were led to believe that these stars collapse in on themselves after their nuclear fuel runs out. But most astronomers believed some physical processes would hold them up.
So in 1926, Ralph Fowler came up with a possible mechanism for the same. So he used the Pauli's exclusion principle, which states that fermions, for example electrons, like we talked about in our last episode of quarks under the standard model of particle physics, where electrons, fermions like electrons cannot occupy the same state. So as matter gets pushed closer and closer together when you crush up a star, the electrons each occupy their own tiny volumes, but Heisenberg's uncertainty principle comes in and says that
it is impossible to know the position and momentum of any particle with absolute certainty, and the more we know one property, the less we know the other.
So as the particles become more and more constrained or compressed in that space, the uncertainty in their momentum and hence their velocity must go up.
So, the more a star is compressed, the faster the electrons will wiggle and jiggle around, and that creates an outward pressure. This electron degeneracy pressure would prevent the star from collapsing completely.
Instead, it would form a white dwarf, with the density much higher than a normal star, and remarkably enough, astronomers have found stars that fit this description, for example Sirius B, if you all know that, but the relief from this discovery was short-lived.
But, soon enough, 19-year-old Subramanian Chandrasekhar, apna desi bhai, he found out that electron degeneracy pressure has its limits. Electrons can wiggle faster and faster, but only up to the speed of light. That would mean that this effect can only support stars up to a certain mass, which we now know as the Chandrasekhar limit. Beyond this, Chandrasekhar himself believed not even electron degeneracy pressure could prevent a star from collapsing. A similar maximum mass for a star which was made entirely of neutrons, was proposed by Soviet physicist Lev Landau.
Now, these neutrons that make up the stars called neutron stars are also fermions, like electrons are fermions, but they have nearly 2,000 times the mass of an electron. Thus, their degeneracy pressure is even stronger. So this is what holds up neutron stars. There was this belief among scientists that even if we didn't know the mechanism, something sooner or later, which we'll find out, would prevent the star from collapsing into a single point and forming a black hole. Because black holes were just too preposterous to be real.
The big blow to this belief came when Robert Oppenheimer,
By the way, look out for an Oppenheimer special coming soon.
thanks a lot, and George Volkoff found out that neutron stars also have a maximum mass. Then, old Oppie and Hartland Snyder showed that for the heaviest stars, there is nothing left to save them when their fuel runs out. And they wrote, this contraction will continue indefinitely.
But Einstein still couldn't believe this. He published his equations in 1915 during the First World War, but he couldn't formulate the exact solution. Then came along Schwarzschild. He read Einstein's paper, and although the war was going on, he was well enough to solve them. So,
Basically, this 41-year-old chap, yeah, I know he's old, went about it with the simplest possible scenario. He imagined a universe where there was a single, perfectly spherical mass. Then, he took it to be electrically neutral and had no spin.
skill issue.
Better than Einstein at least. Bro didn't do this also.
Yeah, on God, bro.
So, then Schwarzschild found the first solution to Einstein's field equations.
Yeah, Einstein didn't expect that it even was possible to calculate the exact solution of the problem in such a simple way.
But shortly after it was published, physicists started noticing two problems with it. There were basically two divide by zero errors, as we would call it. This leads to something with infinite density and no volume, which is called a singularity. This is a black hole.
So, most black holes are born after a big star dies and huge amounts of matter are squeezed together tightly. This pull of gravity is so strong that not even light can escape, and there may be as many as 1 billion of them in our galaxy.
Damn.
Yeah, and we have one big one called the Sagittarius A star, which is a supermassive black hole, and we'll come to the types of black holes later. But they can range up from a couple of solar masses, which means the a factor multiplied by the mass of our sun, to millions of times the mass of our sun. For example, Sagittarius A has a mass of 4 million times the mass of our sun.
That's quite big.
Yup.
So, you might be wondering how it all starts. Let me tell you. It all starts with a star that has at least 10 times the mass of our sun. And it is slowly burning its coal until all its fuel is used up. Then, this fusion process creates radiation and pushes back against gravity, which is basically balancing the star.
But as time goes on, this balance shifts. The star runs out of fuel. Without this radiation from the fusion, the balance of the forces causes the gravity to gain the upper hand on the star and squeezes it much tighter than it was before.
Oh. What happens next is that the core collapses. So the star implodes at a quarter of the speed of light, which is absolutely enormous. And then the core collapses to a black hole in less than a second. In the following hours, the black hole feasts as the rest of the star falls in.
And this implosion that created a black hole is basically something that breaks the rules of our universe. It packs more mass than our sun into a place that's smaller than a mountain.
Damn.
Yup, that's definitely... yeah.
Yeah. So we want to talk about black holes over here a bit.
And we're going to be talking about their parts and their different components, you can say. So we'll first begin with the accretion disk.
Yeah. So the accretion disk, I know it's a very fancy name, but in simple terms, it is a disk of very, very hot gas and dust orbiting a black hole at immense speeds. And some of this material will even pass the event horizon, while some other bits might just blast out as jets.
And these things can go at least up to half the speed of the light, and that's any small collisions within them would cause immense temperatures to be reached. So, as we talked about before, singularities are at the center of black holes, so-called. We'll get on that later, but this is an immeasurably small point at the center that all matter entering it has collapsed into, and everything that has ever passed the event horizon ends up at the singularity, where gravity is practically infinitely strong.
And we come now to the event horizon, which we have heard about a lot. It is basically the boundary between the black hole and the space around it, from which matter and energy cannot escape the gravity basically. And it is an invisible one-way border. once things pass the event horizon, they can never go out again, because you basically need a speed that is greater than the speed of light to escape out from a black hole.
Yeah, and basically when you're at a black hole, that the definition says that the event horizon is the radius at which the speed of light is the escape velocity required to
Correct.
escape the black hole. So anytime when you enter that, that's not possible. So
Yeah.
then we go on to Hawking radiation. So Hawking radiation basically says that there are quantum particles, so like particles and antiparticles. For example, the quarks and the anti-quarks that we talked about in the last video. So they are able to escape the black hole. One of the particles is escaping the black hole, while the other one is sucked in by the black hole.
Yeah.
Thus, this steals the mass of the black hole, and over eons, like basically 10 raised to 67 years or more, which is something our minds cannot comprehend, is when this radiation over time gets stronger and stronger, and the black hole evaporates until it disappears in a huge explosion.
That's quite interesting.
Yeah.
Now,
And that explosion would have the like level of billions of tons of TNT.
ooh. So now I would like to basically tell you something about a spinning black hole. It's a property of a spinning black hole which is called an ergosphere. So it is basically a region around the event horizon where it is impossible to stay still, whatever you want to call it. This is caused by the rotation of the black hole. And since they were born from dying stars, that basically
Well,
was
basically already
yeah, they were
quickly.
spinning so quickly. All black holes spin as well, which of course Schwarzschild didn't include in his calculations.
Yeah, he didn't account for that. So, old chap. So, when one enters a black hole, they don't seem to enter it. Actually, you can, as an outside observer, you can't see them actually enter it.
Yeah.
They seem to stop at the event horizon. They seem to freeze, and this image of them gradually reddens and fades from view.
Yeah, this is what we physicists basically call as a redshift. And this peculiar effect is linked to the theory that black holes can store information on their surface as 2D images, a concept that was explored in Stephen Hawking's latest paper, Black Hole Entropy and Soft Hair.
Yeah, black holes can be said like they can be called as cosmic thieves because they devour everything in their path and they create this infamous paradox called an information paradox, and it challenges our understanding of physics. And in physics, information is sacred. And interestingly, Stephen Hawking's paper provides a possible solution to the same paradox, which was proposed by Hawking himself.
Yeah.
So, fun fact.
Yeah. So if we imagine the sun to be a golf ball of radius, say 2 or 2.1 centimeters, then the Ton 618 black hole,
Which, by the way, is the largest singular entity in the observable universe.
that's correct. The Ton 618 black hole is around 588 meters. Meanwhile, our little planet would be as big as a ball that has the radius half as small as a human hair. So you can basically imagine the scale, the massive scale at which these black holes exist, which is
Yeah.
basically we cannot comprehend such a big scale ever.
Yeah. And we can see like the absurdity of it as well while we're doing that. So, would you believe me if I said that black holes in general have something in common with something very small?
No way. Tell me more about that.
Well, normally black holes are defined by only three properties: mass, charge, and spin. And this is basically saying that black holes have no hair. So that means that they're featureless. So that means that they only depend on these three factors. But recent research, similar to basically Hawking's research,
Yeah.
says that black holes might have hair, which are called soft hair,
Okay.
which are complex features that provide some additional information about the matter that formed them, thereby solving the information paradox. And the thing that they have common with are electrons, which basically are fundamental particles which also only depend on mass, spin, and charge.
So, now while I was reading more about this, I came across this quantum hair theory. And some of the sub-theories within this suggest that quantum mechanical effects could imprint additional information on black holes. and this information could be related to the quantum states of the particles that formed the black hole.
So basically, in simple terms, you're getting the information stored in the black hole.
Yeah.
You're not losing the information.
And there is a famous soft hair theory which is proposed by Stephen Hawking, Malcolm Perry, and Andrew Strominger, and which is basically
This idea, involves software, which involves low energy quantum excitations that could store information on the event horizon of a black hole. Again, addressing the information paradox as we said before. So this again can link to the holographic principle, where it says that black holes can store information on the surface as 2D images, and this says that the event horizon could encode information about everything that falls into it.
So basically,
Let's go back to Schwarzschild.
yeah, a Schwarzschild black hole has no spin,
So that's out.
and then black holes in general have negligible charge.
Okay, by charge.
So we are left with the mass of the black hole.
So are you saying that all Schwarzschild black holes are exactly the same?
No, we forgot about the radius, which is directly proportional to the mass itself.
And thus the only difference is the size of Schwarzschild black holes.
But the radius depends on the mass of the black hole, right?
Yeah, so this only difference is the size and the mass of black holes, Schwarzschild black holes, and rest. Otherwise, if you would see, they're literally the exact same, like
Yeah.
fundamental particles like electrons again, because that's simple. So if you so now there's this constant for every radius. It's called the Schwarzschild radius, which depends on the mass of a black hole. And if you squeeze any object into a sphere with that value, it becomes a black hole.
So, for example, if you compress the Earth into a sphere with a radius of just 9 millimeters, it would potentially become a black hole.
And you can do that for literally any object. It's basically, the idea is that you're compressing a lot of volume into a lot of mass into a
Very
small
small
amount of
volume.
volume. So basically, you're taking a lot of volume and mass, and you're making it, this mass is the same, but the volume reduces. And once that point is reached, which we can calculate using the Schwarzschild radius equation, we'll get that black hole that we always wanted. So let's talk about Hawking radiation again.
So, as we talked about before, particles and antiparticles constantly interact near a black hole, and which lead to a phenomenon called the Hawking radiation, where black holes can lose mass and energy over time.
But this is a very slow process, as we said, and when the last black hole evaporates, it's going to be the last thing ever, and we're not going to be around to see it. So, interestingly, the gravitational effects at the event horizon of the M87 supermassive black hole, which is the first black hole ever photographed,
Yeah.
are weaker than those at the surface of our own sun. So that's pretty interesting, and we can go on to the escape velocity of a black hole, which is
Basically, it is so incredibly high that even light can't escape once it passes through the event horizon.
yeah. But let's get into black holes.
Like, literally.
So imagine you're in a playground.
And you can freely move in any of the three X, Y, and Z planes.
For example, you can jump up, you can bend down, or you can run across the ground.
But you can't move ahead or behind in time.
You can only go in one direction in time, and that's forward.
And now, but in a black hole, space and time reverse their roles. You can go in any direction in time, but only one direction in space.
So basically, a black hole is the ultimate Uno reverse card.
Precisely.
So no matter in which direction you move, in whichever direction you move, it will always lead you closer to the center of the black hole.
Yeah. So, in order to stay alive the longest, you don't need to move at all. Because the more you move, the quicker is your impending doom.
Now, some say that based on this, the singularity is not a place, as we alluded to earlier, but it's an event in time. Specifically, it's something that occurs in the future of any person or item in a black hole. Basically, you never know when it's going to come until it comes, like our future.
Oops, we reached the end. Didn't see that coming, did you?